Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Natasha binti Muhammad Amirul Asrilo, and today I will present for ITT 575 chapter Global Positioning System GPS. Global Position System or GPS is a system where it shows your exact position on Earth anytime and anywhere. In the past, the US Department of Defense uses it for very precise navigation, and in 1973, the US Air Force proposed a new system for navigation by using the satellites, and the system is known as the Navigation System with Timing and Ranging Global Positioning System, or in short, Navstar GPS. The basic of GPS is the GPS satellites are nothing more than a set of wireless base stations in the sky, where the satellites simultaneously broadcast beacon messages, which is called navigation messages. And a GPS receiver measures the time of arrival to the satellites and then uses the trilateration method in order to determine its position. The picture below shows a sample of the broadcast navigation message for one satellite. GPS system segments are divided into three segments, where the first is the space segment, the second is the control segment, and the third is the user segment. The system space segment is a system consists of 24 satellites in the operational mode, where 21 is in use and the remaining 3 are the spares, where it is used for testing. The altitude is 20,200 kilometers with period of 12 hours. Next is the control segment, where it is a set of ground monitoring stations that track the location and the health of each satellite, which includes conditions such as clock error and satellite malfunction. The Master Control Station is located at the Consolidated Space Operations Center (CSOC) at Flaken Air Force Station near the Colorado Springs, and the operational current segments include a Master Control Station, an alternate Master Control Station, 12 command and control antennas, and also 16 monitoring sites. The location of these facilities are shown in the map as shown. These monitor stations measure signals from the GPS satellites (GS), which are incorporated into orbital models for each satellite. The models compute precise orbital data, ephemeris, and GS clock corrections for each satellite. The Master Control Station uploads ephemeris and the clock data to the GS, and then the GS will send the subsets of the orbital ephemeris data to GPS receiver over the radio signal. User segment is the GPS receiver, where the receiver clock is not nearly as accurate as the satellite clocks, so that is taken into account when refining the GPS position. The GPS receiver typically have 12 to 20 channels, which allow them to monitor many satellites at the same time. How does the GPS works? Each GPS satellite transmits information about its location and the current time. All the GPS satellites are synchronized so that the satellite signals are transmitted at the same instant. The control segment ground stations precisely collect this information as the satellites orbit the Earth. And when the receiver estimates the distance to at least 4 GPS satellites, It can accurately calculate its position in 3 dimensions through a method called space trilateration. The accuracy of a GPS determines the position depends on the receiver and the field conditions, which is the location characteristic, the length of time of the location, and also the arrangement of the satellites in the sky. So, the space trilateration method is a method of determining relative positions using the geometry of triangles. By arranging finding distance between one location to another from 3 satellites, we can narrow our position to only 2 points. One of the 2 points is a position too far from the Earth, so we can decide immediately to reject it, leaving the 1 point that is our GPS fixed. And by using the distance from a 4th satellite, we can eliminate the ambiguity if we have accurate receiver clocks synchronized to GPS time, where the time recorded by the GPS satellite. So how does the trilateration methods works? By using a simple 2-dimensional example as shown, so let's imagine we have 3 GPS satellites, each with a known position in space. As you can see, we have satellite 1, satellite 2, and also satellite 3. So really, all the satellites do is to broadcast a signal for your GPS receiver to pick up with a specific time and distance. For example, the first satellite broadcasts a signal that eventually hits your GPS receiver. So we don't know the angle, but we do know the distance. That's why this distance forms a circle equal in all directions. This means that your GPS position could be anywhere within this circle at this specific radius. So what happens when your GPS receives a second signal? Again, this distance is equally broadcasted in all directions until it hits your GPS receiver. This means that the distance could be anywhere on that circle. But this time, we have 2 known distances from 2 satellites. Therefore, with 2 signals, the precise position could be any of the 2 points where the circle intersects. Because we have a 3rd satellite, therefore it will reveal your true location where all the 3 circles intersect. So using 3 distances, trilateration can pinpoint a precise location. Each satellite is at the center of a sphere, and where they all intersect is the position of the GPS receiver. As the position of the GPS receiver moves, the radius of each circle will also change. However, the reality is that in our 3-dimensional world, that GPS satellite broadcasts signals as a sphere. Each satellite is at the center of a sphere, where all the spheres intersect, determines the position of the GPS receiver. How do we know when the signal left the satellite? One of the clever ideas of GPS is that it uses the same code at receiver and the satellite. It synchronizes the satellites and receiver so that they are generating the same code at the same time. And then we look at the incoming code from the satellite and see how long ago our receiver generated the same code. Extensions to GPS are divided into 2, differential GPS and also assisted GPS. Differential GPS is ground stations with known positions to calculate the positions by using the GPS, and the difference fixed transmitted by using the FM radio, and it is used to improve accuracy. However, assisted GPS is put on a server on the ground to help the GPS receiver, and also it reduces the GPS search time from minutes to seconds. Cellular-based GPS application uses handset-based approaches, which is different from the above method mentioned just now. It uses existing cell towers or APS and infrastructure to triangulate the user's location, but not using the real satellites. Cellular-based GPS also uses very accurate clocks to determine the difference in time in which uplink radio signal from user reach different cell sites. It also measures the direction of signal received at multiple towers with respect to antennas of known position to determine the mobile position. At the cost of running radio, it is accurate to a couple hundred feet. It is working only at where it can be covered by cell towers. So GPS here is only the locator. It can calculate where it is according to the cell towers numbers and then find the position on the map, which contains many attributes. So on the map, we can calculate the shortest path between 2 points according the attributes stored in the database. And then it calculates the position many times per second in order to get new position information because of moving. There is also another new app is that it can show the street views and satellite views. For example, Google G1. You can zoom in to see the real environment around you, which this could help people who cannot really understand the map. The GPS application on mobile and PC are shown in the picture. As you can see, we have satellite views on G1, Google Map on G1, and also street views on G1. Other applications of GPS are navigation, surveying and map making, search and rescue, military tracking and guidance, vehicle and pet tracking, cell phone location, tectonic monitoring, and also US nuclear detonation system. So that is all for now. Thanks for watching, and I'll see you next time. Bye bye.